Okay, this is the first video for Chapter 5. In Chapter 5, we're going to be covering several different topics, but all basically related to the first law analyses of open systems. Right, so first, we're going to go ahead and we're going to look at and develop the conservation of mass principle. Then we're going to go ahead and apply the conservation of mass principle to various systems, including steady flow control volumes. We're going to go ahead and apply the first law of thermodynamics as the statement of conservation of energy principle to control volumes, basically open systems, which means that mass can cross the boundary, as opposed to the previous chapter where we are basically covering closed systems where mass does not cross the boundary. Then we're going to identify energy carried by a fluid stream crossing a control surface. And we're going to go ahead and look at the sum of the energy that mass carries with it into the system. And then we're going to solve energy balances for a variety of different types of steady flow devices, such as nozzles, compressors, turbines, throttling valves, mixers, heaters, and heat exchangers, all of which will make sense after the conclusion of this chapter. So before we go too far into anything, let's start with the conservation of mass. The amount of mass flowing through a cross-section per unit time is denoted as mass flow rate, or m dot. And basically, what it comes to, if I were to sum up this whole slide, which is what I want to do, into one statement, it's basically saying an integration of density times a velocity that the fluid is flowing at, and I integrate that over the changing area of the cross-section. That would be designated as mass flow rate. Now, in many practical applications, we can make the following assumption. We have one-dimensional flow, which means the fluid is flowing in one direction. At any point, all the properties are uniform across the cross-section, and that the properties have a bulk average. Right, so let's take this for example. You have a pipe, right? You have water flowing in a pipe. We can all assume that the velocity of the fluid is 0 at the inner wall of the pipe, but at a maximum in the center of the pipe. This gives this change in velocity between the wall to the center is called a velocity profile. What we're going to do is assume that the velocity through the pipe flows at an average velocity. We're also going to assume the area through the pipe is constant. So what happens is that integration of the mass flow rate from the prior slide ends up just becoming density times velocity multiplied by the cross-sectional area. That is the basic of what we're going to be looking at for conservation of mass. Now, volumetric flow rates, a little bit different. Volumetric flow rate, which is designated as V dot, again, if I were to integrate the velocity over the area, assuming constant area, I get that my volumetric flow rate is equal to velocity times area. So mass flow rate equals density times volume flow rate. Or, if you remember, specific volume is 1 over density. So I can actually get my mass flow rate to equal the volume flow rate divided by specific volume. That's an equation that we are going to be using significantly in this class. So, what is this? What are we getting to with this? We're going to go ahead now and lay out the conservation of mass principle. It is one of the most fundamental principles in nature. And the conservation of mass principle reads the following. The net mass transfer to or from a control volume during a process is equal to the net change in the total mass. So here it is. I have the mass entering a control volume minus the total mass that leaves a control volume has to equal the net change in mass in the control volume. If I were to write this out a little bit more compactly, I get mass in minus mass out equals the change in mass of the control volume. It can also be in rate form, that the rate of mass entering minus the rate of mass leaving has to equal the rate change of the mass of the control volume over time. These expressions are referred to as mass balances, and they are valid for any system undergoing any process. I can expand this also to do a mass balance for multiple inlets and outlets, right? So if I have several mass inlets, I get all the sum of the mass in minus the sum of the mass out equals the change in the mass of the system. I could also write this in rate form. The sum of all the mass flow rates in minus the sum of all the mass flow rates out equals the total rate change of the mass flow rate over time. So when the properties at the inlets and exits, as well as within the control volume, are not uniform, then you can express it in differential form, which we're not going to cover much here. But these are the two basic forms of this conservation of mass principle. The sum total of mass in minus the sum total mass out equals the sum total change in the mass of the system, or the sum of the rate of mass in minus the sum of the rate of the mass out equals the rate change of the mass of the system. Now, this can simplify for steady flow processes, right? If I have a steady flow of mass in and a steady flow of mass out, the mass of the system is not changing, therefore the change in mass of the system is zero. Remember, I did not say that the mass of the system is zero. I said that the change in mass is zero if I have the same mass going in as I do going out. That means the change in mass of the system is zero. Now, I'm going to ask you a quick question here. If I have, can I repeat this for for volume flow rate? If I have a steady flow system, can I also say that the sum of the volume flow rates in is equal to the sum of the volume flow rates out? And the answer is only if if the fluid flowing has a constant density, right? Only if it is incompressible. Only if it's incompressible. If I'm dealing with an ideal gas, for example, right? This is only for incompressible systems. Because if you think about it, mass flow rate equals volume flow rate divided by specific volume. For an ideal gas, my specific volume is changing constantly. So if my volume flow rate equals mass flow rate times specific volume, my mass flow rate is conserved according to the conservation of mass. For a steady flow system, the mass flow rate in has to equal the mass flow rate out. But if I have different pressures and different properties in my inlet and my outlets, my specific volume for an ideal gas is changing. Therefore, it's also changing the volume flow rate. Therefore, this is not true. Not true for ideal gases. But it's true for incompressible substances. The conservation of mass is always true, but I can't extend that to a conservation of a volume flow rate if it is compressible. It can be if it's incompressible, like fluids. You can assume to be incompressible, but it is not true. The sum of the volume flow rates in is not equal to the sum of volume flow rates out for an ideal gas. The sum of the mass flow rates in is equal to the sum of the mass flow rates out for a steady flow system for ideal gases. That is true, but not for volume flow rates.